Many thanks for organizing for the kind invitation. It's a great pleasure for me to give a talk in this series of seminars on scalar curvature and more, not only scalar curvature. I like the title of this series. Okay, so today I would like to talk about joint work about Alessandro Cucinotta, who is a last year PhD student, and he will be on the job market for postdocs from next fall. And it's about studying manifolds of almost non-negative Ricci curvature, and then we have some positivity on the sum of the smallest k eigenvalues of the Ricci curvature. So that's the framework. So the setting is we consider manifolds, Riemannian manifolds of dimension n, and such that the Ricci curvature is non-negative or almost non-negative, so bigger than minus delta, where delta is a small positive, and the sum of the lowest k eigenvalues of the Ricci tensor is positive, say bigger than 1. Of course, having R1 bigger than 1 means that the Ricci is bigger than 1, and when k is equal to n, this means that the scalar curvature is positive. So this Rk is an intermediate condition of positivity between positive Ricci and positive scalar curvature. Okay? And as a matter of terminology, we will call this Rk kth scalar curvature. So positive R1 is positive Ricci, positive Rn is positive scalar curvature. Okay. So the question that we're interested in is how does a manifold which satisfy this almost negative Ricci and positive k-scalar curvature look like from far away, when we look this manifold from far away? So this kind of question was proposed by Gromov in a very influential paper of 1986, who conjectured that if one has a manifold of with non-negative Ricci and with positive scalar curvature, so k is equal to n, then the volume of large balls grow in a controlled way by the radius to power n minus 2. So we expect an n minus 2 dimensional behavior at large scales for positive scalar curvature and, say, non-negative Ricci. For intermediate values of k, instead, Gromov in the same paper showed that if one has a positive k-scalar curvature and some stronger curvature assumption, namely bounded sectional and bounded unitive radius, then the volume of large balls is controlled by r to the k minus 1. Okay, so we expect that that positive k-scalar curvature implies an k minus 1 dimensional behavior at large scales. Okay, so in this joint work with Cucinotta, we obtain some good description for k equal to 2. So when we have a positivity condition on the sum of the smallest two eigenvalues of the Ricci, and then some weaker result that I'm going to discuss in the end for larger values of k. Okay, so the plan of the journey of today is I will first state the main result for almost negative Ricci and positive sum of the smallest eigenvalue of the Ricci. I will sketch the proof of this result, and then I will briefly mention the result for Eiger k. So for when you have a non-negative Ricci and the sum of the smallest k eigenvalues of the Ricci is positive and k now is larger than 3. Okay, so let's get started. Oh, this went too far. I don't know what happened. This went up to the end, so let's go back. Okay. Good. Okay. So let's start with the first main statement. So the main result that I would like to discuss is the following. Take a dimension n, at least 3. Then there exists some constant c and delta, c very large, delta very small, such that if an n-dimensional manifold has Ricci band below by minus delta, and sum of the smallest eigenvalue of the Ricci is bigger or equal than 1, then there exists a connected one-dimensional manifold, let's call it I, possibly with boundary, so an interval or a half line or a line or an S1, and a distance preserving embedding phi from this one-dimensional manifold into M, such that the manifold M is contained in the C-neighbourhood of this image of phi of I. So in a picture is this. So here we have this one-dimensional manifold I, could also be a circle. And we have this isometric embedding phi of I, such that the manifold M is contained in the C-neighbourhood of phi of I. Okay? So now let me briefly stress that this phi is not just preserving the Riemannian metric, but is really preserving the distance. So this forbids like behavior like an helix. So an helix which is spiraling on a cylinder is forbidden. So it is really like a line. It is not just a geodesic. Okay? So this phi of I is really an isometric embedding globally. Okay. So now let's try to understand the outcome of the statement. Okay. So now I would like to discuss what does it mean for a metric space to have to admit such an embedding. So when does a metric space XD admit a isometric embedding, distance preserving isometric embedding of a one-dimensional manifold I, such that the space is contained in the one neighborhood of this phi of I. Okay, so let me just discuss a couple of examples first to get a grasp. So when we have a cross, say, of length at least 2, then the property fails, because say you can embed this one-dimensional manifold either as a segment like this, or like this, or a permutation. And in both cases, you cannot find a one neighborhood which contains of this red part which contains the whole space. And the same thing happens. So in other case where a metric space is not contained in the one neighborhood of phi of I is an S1 of radius 2, where you add the diameter. Then in this case as well, the property fails, because if you have a segment, then you can easily see that the manifold is too far away. The only non-trivial case maybe is when you have the embedding of an S1. This could either be embedded as the full circle, but then you have the center of the circle, which is a distance 2, so it's not the distance 1, or you embed it in this red part, but then you have this lower part where you have a point of distance bigger than 1. Okay, so just to have an idea of two basic examples where the property fails. Instead, some example where the property hold is like if you have a segment, say of length 2, and you add some small hair, this is still fine. Or you have, say, a circle, and S1 of radius 2, say, and you add some small hair, and you can also add some topology, say, a Hawaiian ring here we are adding, but it must be very small, say, smaller of scale 1/2, say. Okay? Okay, just to get a grasp of what this conclusion means. Okay, so again, the statement of the theorem is that if you have a manifold of almost negative Ricci and positive sum of the first two eigenvalues of the Ricci, then basically it looks one-dimensional. It contains a distance preserving the bending of a one-dimensional manifold, such that the whole manifold is contained in the C-neighbourhood of this embedding. Okay, so actually we prove a stronger result where we instead of having a uniform positivity condition on the R2, on the sum of the smallest eigenvalues of the Ricci, actually is enough to ask for an interval condition. So it's enough to ask that you have an almost negative condition pointwise on the Ricci, and an integral positivity condition on the sum of the first two eigenvalues of the Ricci. So let me read it. So we take the sum of the smallest eigenvalues of the Ricci. We take the minimum with 2. Okay, so basically we are truncating. If this is very positive, we just truncate at 2. We take the average on the balls of radius 1, and then we want this to be bigger than 1 for every x. Okay? So this allows some small regions where R2 could be very negative, but the integral must be positive. Okay? And again, under this assumption, we have the same condition, which is that, say, from far away, the manifold looks like one-dimensional. The manifold is contained in a neighborhood of a one-dimensional manifold. Okay? So now let me stress that the statement fails without lower bound on the Ricci. So one could ask, is it really needed, this lower bound on the Ricci? Yes, because indeed one can do some gluing, or following construction by Wolfson, which builds on top of the celebrated gluing construction on a scalar curvature by Gromov and Lawson. One can check that if you don't have this lower bound on the Ricci, you can build kind of a cross manifold where R2 is positive. Okay, and we just check and we just saw that this cross manifold does not satisfy this condition. Okay, and this statement actually has some strong geometric consequences on manifold which satisfy this assumption. It implies that such manifold have linear volume growth. That's not hard. That's basically because if you have a lower bound on the Ricci, you control the volume of metric balls, and then you can patch your manifold with control metric balls, since you are in a bounded strip around a one-dimensional manifold. It implies that the first Betti number of the manifold is bounded by 1. That's why, well, because both conditions lead to the universal cover. And then you can check that if the Betti number is bigger than 1, then you have two directions where the universal cover must go to infinity. And this contradicts the fact that you are in a one dimension, that you are basically one-dimensional from large scales. And it also implies that if the manifold M is non-compact and there is curvature properties, then the fundamental group must be finite. Okay, and again, is because if the manifold is non-compact, then you have at least one ray, so you have one direction which goes to infinity. And if you have infinite fundamental group, then you can go to the universal cover, and you would have another direction where the universal cover go to infinity. But universal cover satisfies this condition, so must be basically one-dimensional from large scales, and then you get a contradiction. Okay, so just to get an idea of the consequences of these properties. Okay, so let me discuss some related results in low dimensions. So there are some results for manifolds in lower dimension. So Gromov in 2019 proved that if the dimension is equal to 3, and you have positive scalar curvature, say scalar curvature bigger or equal than 1, then there exists a topological graph gamma and a continuous embedding, call it F, from the manifold to gamma, whose fibers have diameter bounded by a universal constant, which means, in other terms, that such manifold has bounded one unison width. Okay, and here let me say that the strength of this result is that there is just an assumption on the scalar curvature and no other assumptions, say on Ricci or any other curvature. So it's a beautiful result by Gromov. And okay, some other result is one by Munteanu Wong and Chodosh Listriker, who gave a different proof of this previous result for Munteanu and Wong, who proved that if n is equal to 3, so if you have a three-dimensional manifold with non-negative Ricci and the scalar curvature bigger or equal than 1, then one has linear volume growth at infinity. And this is this confirms the previous conjecture that I mentioned in the beginning of the talk by Gromov in dimension 3. And the conjecture is that one should have this n minus 2 volume growth for any dimension if Ricci is non-negative and scalar positive. Okay, and then some more recent research by Antonelli and Xu and Zhou of last year, who proved that if the Ricci is non-negative and the B Ricci is bigger or equal than 1, then one has linear volume growth at infinity if the dimension is at most 7. Okay, so now this B Ricci, I say, let me not enter into the technicalities, but is a condition which is equivalent to having positives, say, bigger than 1/2 two-scalar curvature. So in dimension 3, having positive B Ricci is equivalent to having the sum of the first two eigenvalues of the Ricci being positive. But in higher dimension, the two conditions have non-trivial intersection, but they are actually different. Okay. Okay, so now let me recall again the statement, what we want to prove. Now I want to sketch the proof of this main result. So let me recall it. So any dimension, we have Ricci almost non-negative. We have some of the first two eigenvalues of the Ricci is positive, say bigger or equal than 1/2. Then we want to prove that there exists an isometric embedding, a distance-preserving embedding of a one-dimensional manifold into M, such that M is contained in the C neighbourhood of this image, phi of I. Okay, so the proof is split into two steps. The first step is a purely metric property of minimizing geodesics, which will imply the conclusion. And the second step is to show that this curvature assumption imply this metric property. Okay. Now let me state this metric property. So what we call segment neighborhood property. So we say that a metric space XD satisfies the segment neighborhood property, and we call it SMP for short, at some scale R, if the following holds. So let me first state it in words, and then we look at the formula. So we want to say that every time that we have a very long segment, so of length, say, at least 2R, and every time that we have a point X, which projects in the middle part of the segment, then this point must be actually close to the segment. Okay, that's the idea of this property. So it says that every time that we have a segment which is long, so longer than 2R, and every time that we have a point X, such that the distance from the point to the segment is equal to the distance from the point to some point LT, where T is between R and length of L minus R, so this point LT is in the middle part of the segment, then the distance from the point to the segment is small, is controlled, is less than R over, say, 100. Okay? Okay, so just a remark. So this symmetric property is related to some previous work by Vyshakapovich on tripods of a few years ago. But yeah, let me just stick to this segmentable property for this talk. Okay, so the question is, what do spaces which satisfy this segmentable property as scalar look like? So what is this property telling us about the metric space? So let's go back to the example that we saw in the beginning of this talk. So let's take this circle over radius R, and we add the diameter. Okay. Now this circle, so this metric space is geodesic. It's very nice, but it does not satisfy the segment neighbor property. So why? Because we surely have a segment of length less than 2R, which is this red part here. But we have one point, which is the center of this circle, X, which is a distance R from this segment. It projects in the middle of the segment, but is not closer than R over 100. Okay, so these kind of spaces do not satisfy the segment neighbor property. A space which does satisfy the segment property is instead say, an S1 of radius R. We can add some small hairs, some small spikes. They must be not too long. And we can also add some crazy topology, but at small scales. Okay, so this space does satisfy the segment neighborhood property. So observe that this segment neighborhood property gives some control on large scales, say, of scale larger than 2R, say, but gives no control on small scales, on scales, say, smaller than R over 100. Okay, so we can have a lot of topology which is hidden at small scales. Okay. So with Cucinotta, what we prove is that this metric property, so this segment neighborhood property, implies the final part of the statement. So if a proper geodesic metric space satisfies the segment neighborhood property, then there exists a one-dimensional manifold I, possibly with boundary, and a distance-preserving embedding phi from this one-dimensional manifold to X, such that the metric space X is contained in the 200R neighborhood of this phi of I. Okay, so from far away, this metric space looks like one-dimensional. So it is in a controlled neighborhood of a one-dimensional manifold. Okay. So now, in order to conclude the proof of the statement for manifolds, what we need to show is that if we have an n-dimensional manifold with almost negative Ricci and say R2, sum of the smallest two eigenvalues of the Ricci bigger or equal than 1, then this manifold satisfies the segment neighborhood property for some scale. Because then if we show that the segment neighborhood property holds, then we can apply this result and get the one-dimensional manifold. Okay, and the proof of this theorem here is so it needs a little bit of care, but is playing with channel inequalities. Okay, so it's not too deep, but it needs some care. Okay, so now we want to show that the curvature condition imply the segment neighborhood property. So for simplicity, let me assume that the Ricci is non-negative, okay? And we argue by contradiction. So we assume that there exists a sequence of manifolds, Mi, and scales are I. This manifold have non-negative Ricci, and they have some of the smallest eigenvalues of the Ricci bigger or equal than 1, but the segment neighborhood property fails at scalar I. Okay, so what does it mean that the segment neighborhood property fails at scalar I? It means that we can find long segments, so these Li are long segments of length bigger or equal than 2R, and we can find points, xi, which project in the middle part of this segment, but these points are far away, but from the segment. So the distance from this point to the segment is bigger than Ri over 100. And this Ri is going to infinity. Okay? So now, since we have non-negative Ricci, we can apply Gromov compactness theorem, which tells us that this pointed manifold convert to some limit metric space Y in the pointed measurement field of convergence. And we can pass to limit these longer segments and obtain a line L, which is the limit of these longer segments Li. Okay, now this limit space Y is a limit of manifold with non-negative Ricci. So we can apply the splitting theorem, which was proved for Ricci limit spaces by Chiller-Colding, and infer that this limit space Y splits off an R factor isometrically. Okay, very good. Now let's see what we can say on this remaining factor Y prime. So now remember that these points xi are at larger and larger distance from the line Li. And so pass the limit, we can prove that this Y prime will contain a ray, which is a limit of the segments of xi pi, and then this Y prime is non-compact. Then by a diagonal argument, which I don't detail, but basically instead of blowing up, instead of taking the pointed limit at pi, you take the pointed Gromov limit, say, at the midpoint of this segment, you can prove that this manifold with the center point qi, say, in the mid of this segment xi pi, will converge to a metric space which splits off R2, so two Euclidean factors. Okay, so you can iterate the splitting theorem. Okay, good. So what we got that if the segmental property fails for this sequence of manifold at scales Ri, which are larger and larger, then these manifolds, which have non-negative Ricci and have sum of the smallest eigenvalue bigger or equal than 1, converge to a metric space which splits off two Euclidean factors. Okay, that's what we got so far. Okay, so now to conclude the proof, it's enough to show that the curvature assumption, the fact that the Ricci is non-negative and that R2 is bigger or equal than 1, prevents convergence to a metric space which splits two Euclidean factors. And how we prove that? We prove that by showing a kind of continuity of the integral of the sum of the smallest two eigenvalues of the Ricci under Gromov convergence. Okay, so what we show, of course, not okay. What we show is that if we have a sequence of pointed manifolds, MI, with center points pi, which have non-negative Ricci and which converge to some metric space which splits off k Euclidean factors in pointing of sense, then the average integral on the ball of radius 1 centered in this point pi of the sum of the smallest eigenvalues of the Ricci truncated by 1 from above converge to 0. Okay, so that's intuitive. Why? Because the fact that the Ricci is non-negative is saying out that all the eigenvalues of the Ricci are non-negative. Okay, so this guy here from below cannot go below 0. Okay. What is saying is that if you split off at Rk, then the smallest eigenvalues of the limit of the Ricci, roughly, the limit may not be smooth, but they're going to be 0 because all the others are going to be positive, roughly, if you believe in some synthetic curvature condition of this limit. So roughly, what you expect that this limit space is Rk equal to 0 if you split k Euclidean factors. And this is saying that if you converge in polynomial sense, then the average must go to 0. So it's a continuity result for this integral to the limit in a rough sense. Okay? So it is something that one can believe. Okay? So let me also mention that if k is equal to n, so if you converge, if the manifold Mi converges to Rn, where n is the dimension of the manifold, and one has in addition some non-collapsing assumption, then Wang, Xie, Zhu, and Zhu show that no limit can split Rn minus 1. Okay, so one can improve the dimension by 1 if one considers the scalar curvature by adding a non-collapsing assumption. Okay, so now let me give you an idea, a very, say, sketchy idea why this theorem should be true. Okay, so a sketch of why, if you have a sequence of manifolds, Mi, which have non-negative Ricci, and some of the smallest k eigenvalues of the Ricci bigger or equal than 1, they converge to something that splits off k Euclidean factors. Then we want to show that the average of the average integral of the sum of the smallest eigenvalues of the Ricci truncated by 1 converges to 0. Okay, so the building block of the argument are delta splitting maps, which were as in the work of Chirk-Holding. So what we know from Chirk-Holding work is that if you have a manifold M with almost negative Ricci, and this manifold contains a ball, say of radius 10, which is Gromov close to a ball of radius 10 into a splitting, so into symmetric space, which splits isometrically Rk, and then you have symmetric space Y. Then there exists some Gromov map U from the ball of radius 5, say the ball of half of the radius, inside the manifold, with values into the ball of radius 5 in Rk, in the Euclidean space of dimension k, such that the gradients of this function u are almost orthogonal. So ui and uj are the are the ith component and the j component. So the gradient of ui times the gradient of uj minus delta ij is small in an integral sense. So this should be understood as, in integral sense, the gradient of u is orthogonal, and the Hessian of u is small in an integral sense. So this is what Chirk-Holding tells us. Okay, now we plug this ui into Bochner formula. We multiply by some good cutoff function that we know that exist. We integrate by parts with some computations, and we get that for each I, if we take the average over the ball of radius 1 of the Ricci evaluated on grad ui, grad ui is controlled by the Hessian of ui. Okay? And we know that the Hessian of ui is small. Okay? So now let's consider the eigenvalues of the Ricci, lambda 1, lambda n. The Ricci can be diagonalized by an orthonormal frame. And so, since the gradient of ui are orthogonal, we expect, so we can rotate them in a way that the gradient of u1 is almost the first eigenvector of the Ricci. Gradient of u2 is almost the second eigenvector of the Ricci, and so on. So this would be true if we had here a uniform smallness of grad ui, grad uj minus delta ij. So if instead of L1 smallness I had the uniform smallness, this would be true. Here I'm cheating. One has to do some work to overcome this cheat, but that's the basic idea. Okay, so but just by this argument, okay, even if it's not precise, you can do this argument on a set of large measure, basically. Good. So assume that you can rotate this u such that each of the gradient of ui is almost an eigenvalue, and you ordinate this eigenfunction from 1 to k. Good. Then now you sum up this this second display math from 1 to k. So what you get is that the sum of from 1 to k of Ricci, grad ui, grad ui, since ui are almost orthogonal, this is going to be roughly the sum of the first k eigenvalues of the Ricci, which is roughly Rk. Okay? And this is bounded by what? It is bounded by the Hessian, by the sum from 1 to k of the Hessian of ui, which was small by 1. Okay? So this is going to be small. Okay? So this is giving that the integral of Rk, of the smallest eigenvalue of the Ricci, is small. And this is what we wanted to show. We want to show that this goes to 0 if we converge to a splitting of Rk. So where I've been cheating, the cheating is that what we have is integral estimates, and what we need to make this work is a pointwise estimate. So how to make the argument work is you first turn these integral estimates into pointwise estimates on large sets, and then you use some covering arguments to close the argument. Okay, and when you do this calling arguments, you always have some small sets which remain uncovered, and is where you need to truncate by one this RK. Otherwise, the argument, as I told you, would give smallness of RK without cutting by one. So, but that's just a rough sketch in order to you to have an idea. Okay, so this basically concludes the sketch of the proof for the main result, because this prevents the manifolds converge to an RK, and this concludes the contradiction argument. Okay. So now I would like to discuss some further results for any dimension and for any k from 1 to n.
Perhaps
Yeah,
before the
yeah,
further results,
yeah, sure.
we can allow anyone online who wishes to ask any questions
Ask
at
some
this
questions.
point.
Yeah, thanks, Christina. Sure.
Does anyone wish to ask?
Here was the result.
So I have sort of basic question concerning one of your first slides.
Yeah.
Namely, so when we have scalar curvature bound positive, then roughly the manifold looks n-2 dimensional.
Yeah.
And if the sum of the first k eigenvalues is positive, then it's k-1
Yeah.
dimensional. But this holds just for k smaller than n.
Correct.
So why is this gap? Why is there something
Right.
happening between n-1 and n?
Yeah, basically you gain one for the scalar curvature, and you can see that already for products. So I think that the easiest way of seeing it is take S2 cross R. So S2 cross R, you have positive scalar curvature and positive R1. So from positive scalar curvature, you get say the sharp thing, but you have also positive Ricci curvature, and you don't gain one extra dimension. So basically, yeah. But so the point that with the scalar, since so for the scalar curvature, you get n, and basically is that you see curvature when you have products, you see curvature from 2 on, because if you do a product with S1, you have no curvature, but you have curvature just from 2 on. While from 2, 3, 4, then every time that you add one, you see one more eigenvalue of the Ricci. So you see this really on example easy Sn cross Rk. Thanks for the question. Okay. If there's no further question, thanks for that. Okay, so now let's discuss some results about tangent cones at infinity. Okay, so what is a tangent cone at infinity? I think that most of the people here know, but let me just recall it. Okay, so consider a pointed manifold with non-negative Ricci. Then by Gromov compactness, we know that if we scale down the manifold by some rescalings Ri, which go to infinity, then this sequence of manifolds is precompact in pointed measure of convergence, and then it will convert to some pointed metric space X. So this space X is called blowdown or tangent cone at infinity of M. And just a very basic example, if M is a product, so is R times N, where N is the compact manifold, then when you blow down, you in the limit, you are shrinking the compact factor, and you're going to see just R in the limit. Okay. Now, of course, this tangent cone at infinity X depend just on the large-scale geometry of M. So if you perturb M on a compact set, you will not see that on tangent cone at infinity. In general, the tangent cone at infinity might depend on the chosen sequence of rescalings. This was already understood by Perelman, who gave some example of a manifold with positive Ricci and where you have non-unique tangent cone at infinity. And in general, even if we call it a tangent cone, it may not be a metric cone. Indeed, Chigall-Colding gave some example where the tangent cone at infinity is not a metric cone. Okay? Nevertheless, Chigall-Colding proved that these tangent cone at infinity are rectifiable as metric spaces. For almost every point, they have a Euclidean tangent. And Colding-Naber proved that this Euclidean tangent have a well-defined dimension. So the dimension of these Euclidean tangents don't change from point to point. Okay? So this means that every tangent cone at infinity will have a well-defined dimension called the rectifiable dimension, which is the dimension of the tangent spaces at almost every point. Okay? So with Cucinotta, what we proved is that if you have a manifold M with non-negative Ricci and positive K-scalar curvature, so the sum of the smallest eigenvalue of the Ricci is at least 1, say bigger than that, bigger than epsilon, doesn't, here we don't need 1, then any tangent cone at infinity of M has rectifiable dimension at most k-1. Okay, so this is very much in accordance with the result of Gromov that I recalled in the beginning, which said that if you have a manifold of non-negative Ricci, if you have a manifold with positive Rk, and then there were some stronger geometric assumption on bounded sectional curvature and bounded infinity radius, then at large scale, one has a k-1 behavior. So you have some k-1 dimension popping up in the limit. And here, so there in the result by Gromov was at the level of volume of large balls. Here we see the k-1 dimension at the level of structure of the tangent cone at infinity. Is the dimension of the tangents of the blowdown of the manifold. Okay, so actually, so here I'm giving the statement in the cleanest way, but actually we can relax quite a bit the assumption. So instead of asking the sum of the smallest k eigenvalue of the Ricci to be bigger than 1, it's enough to ask that the sum of the smallest k eigenvalue of the Ricci multiplied by the distance from a base point to some power alpha between 0 and 2, take the limit for x go to infinity, this is positive. So basically, this is saying that Rk is bounded below by a positive function, which goes to 0 in a controlled way. It goes to 0 at not faster than distance to power 2. Power 1 over distance to power 2. Okay, so this is still pointwise, but actually we can even go further in relaxing this assumption. We can even ask a asymptotic interval condition of positivity on the smallest eigenvalues of the Ricci. So it's enough to ask that the following odds. Okay, so take any L positive. L is a positive number. Okay, so take take Rk, the sum of the smallest eigenvalues of the Ricci, multiply by the distance from the origin, R to the alpha, truncate by L, okay, and then take the average over the ball of radius R and let R go to infinity, and then you ask that this is equal to L. So this is saying that roughly at large scales, Rk is going to be positive in an integral sense, but it may happen that Rk is negative or even very negative just on regions which are small in volume in comparison with the volume of the ball of radius R. Okay, so it's a bit complicated to write down, but it's an integral condition of positivity type on the smallest eigenvalues of the Ricci. Okay, and then again, you get that and tangent cone at infinity have rectifiable dimension at most k-1. So you have kind of a k-1 dimensional behavior of the tangent cone at infinity. Okay, so why 2? Why this alpha between 0 and 2, both here and in the integral result? Well, because for alpha equal to 2, the statement fails. And the counterexample is very easy, is the paraboloid in R3, which has non-negative, actually it has positive Ricci. It has non-negative Ricci, sorry, it has non-negative Ricci. It has positive R2, but it has, when you blow it down, it has, you get a line, and if you count here, you would get 0. So you would expect dimension 0, but the blowdown is a half line. And so you cannot put up alpha equal to 2. Okay? So for k equal to 1, k equal to 1 is Ricci. So R1 being positive means Ricci being positive. So here what we ask is either a decay of R1 in pointwise sense, or in this more general form is an integral positivity condition on the Ricci. Then by the same result, we get a compactness of the manifold, which is very much in the same spirit of a celebrated result by Gromov-Taylor. So basically, what Gromov-Taylor proved in 82 is that if you have a complete manifold with non-negative Ricci and with the Ricci bounded below by a function which goes to 0, which is positive and goes to 0 at most as 1 over distance squared, then actually the manifold is compact. Okay, and they assume a pointwise lower bound on the Ricci, and we get basically the same conclusion. Say that the manifold, if you have an integral asymptotic lower bound on the Ricci, then the manifold must be compact. Okay, so is an integral relative of the theorem of Taylor result. Okay, and if instead of say when k is equal to n, okay, so when we have scalar curvature, so as Bernard was saying before, one could expect to improve the dimension by 1 further. Okay, so we could expect that the tangent cone at infinity is rectifiable of dimension n minus 2, and we can prove that under an additional curvature assumption, which is the n minus 2 Ricci curvature. So basically, we ask the positivity of an intermediate curvature condition between Ricci non-negative and sectional non-negative. So the easy statement would be sectional curvature non-negative and this decay on the scalar curvature, then the tangent cone at infinity has rectifiable dimension at most n minus 2, so you gain 1 more. But actually, you don't need non-negative sectional, you just need an intermediate condition between sectional non-negative and Ricci non-negative, which is the n minus 2 Ricci being non-negative. Okay, and I think this is all, and I wish to thank you very much for your attention.